Okay. Well, how was the quiz? Okay. I'm grading second periods. Of course, unfortunately, not going to get any lower than a zero. I got several zeros out of second period, but I now have a new highest grade, 103. Okay, so now that's the highest grade, and pretty much you have everything in between. So what I'm noticing so far is that either people have a pretty decent idea of what they're doing, or they have absolutely no idea what they're doing. It's we're on opposite ends of the spectrum. So if you are needing help, you got to come in as soon as possible. Okay, now you'll have till next Friday to retake. I'm going to take some time in class tomorrow to go ahead and talk about the quiz, hopefully fill in any gaps, but we are going to go ahead and move on. Okay, we have our new focus activity, number 7. I thought this would be a pretty easy thing to do after the quiz, just a little bit of algebra skill, kind of a win. All right, so it says a maximum mark of 5. So for those of you who continue in calculus, you're going to be taking, the AP exam at some point, or if you're in IB, you're going to be taking exams in there, and you're going to see exams that are marked like this, and they're going to be 90-minute exams at 90 marks. So a good way to think about it is this means that this particular question was worth 5 points, and it's broken down, into A and B. But it's really good to think about it in terms of your time. So at most, I would say this problem, you could spend 5 minutes on it. But hopefully, it wouldn't take you the full 5 minutes if you were taking it. Let's see. We got function f, which is a times x minus h squared plus k, which is what form? That's vertex form of a parabola. So we're given the vertex of the graph is at 2, 3, and the graph passes through the point 1, 7. Write down the value of h and k. All right, well, what is h? K is what? 2, there we go. And k is 3. There we go. It was just right in front of me. The vertex is always labeled as hk because x and y are what we call generic variables that have to be there as part of the equation. Okay, so that one's pretty easy. We got 2 points. But now find the value of a. So I want to find the scale factor responsible for the dilation. Well, what can I do? Yeah, just plug it in. If you take a look, we already know the values of h and k. We have him and him. Do we have an x and a y? Yeah, we were provided that as well. So I've got 4 of the 5 variables in my equation. So it's just substitution and isolating the variable. So let's see, instead of f of x equals, I will say 7 equals. We don't know what a is just yet, times x minus h. So x being 1 minus h being 2 squared. And it looks like I'm going to add what? 3. Okay. Well, what is a 1 minus 2 squared? 1. So that makes it easy. That means just a plus 3 has got to equal 7, so a should equal 4. So this should be a vertical expansion or a vertical stretch by a factor of 4. Okay. Good, good, good. Now, how many focus activities do you have at this point? You've got 3. We have already turned in numbers 1 through 4. We are not dealing with those again, but next week on Wednesday, you're going to be turning in numbers 5 through 8. Okay, so right now you've got 5, 6, 7. On Tuesday, after the long weekend, you'll get number 8, and then we'll turn those in on Wednesday. Should be a guaranteed good grade because there's only 2 weeks left in the 6 weeks. Okay, 2 weeks from tomorrow, I'm going to be submitting the grades for the first grading period. And what do we have before that? You have a major exam next week, which will cover the exact same material that we just had on our quiz. Okay, so please, please start taking the opportunity to study. Come in if you need help, whatever we need to do. Okay? All right. Well, let's go ahead and take a look at this. Before we move on with our next unit, which is going to cover composition of functions and inverses of functions, I thought it'd be a good idea. Let's go ahead and put some closure on end behavior and limits. And we'll go ahead and do that using the continuity test. Because I think some people could still, benefit from some practice on this. Well, what is continuity? The graph of a continuous function has no breaks, holes, or gaps. Excuse me. Don't know you. Okay. All right. Now, let's see here. I've mentioned this briefly, but it was weeks ago. I said if you're trying to figure out, if a graph is continuous or not, a good rule of thumb, if you can draw the entire graph without lifting your pen or pencil off the paper, it's going to be continuous. It's these discontinuities that we've looked at before that make it non-continuous, or we'll say discontinuous, depending on what kind of discontinuity it has. All right, but there is a test algebraically to go ahead and determine that at specific values. So what's this say here? One condition for a function f of x to be continuous at x equals c is that the function must approach a unique function value, we're talking about y, as x values approach c from the left and right sides. The concept of approaching a value without necessarily ever reaching it is called a limit. Okay, if the value of f of x approaches a unique value L as x approaches c from each side, then the limit of f of x as x approaches c is L. Okay, how many people love mathematical definitions as much as I do? Okay, they make so much sense when you first read them. Let me see if I can kind of break that down and help you understand. Let's say we got a graph here. Okay, so this is illustrating what we just verbalized. So c is some x value, right? So if I were to go ahead and plug in c to whatever this function is, this value, the coordinate would be c and then f of c, right? F of c would represent the y value once I substitute that x value of c in there. Well, all we're saying is that if I approach this value of c from either side, I should be approaching the corresponding value of y from both sides as well. Okay? As I get closer to a particular value of c, a value of x, I get closer to what they're calling a unique value L, which represents your y's. They're just using different variables here. So let me see if I can make it a little more concrete for you. Let's say I give you a linear function. Okay? How about something really easy, like how about negative 2x plus 5? Negative 2x plus 5. Okay? So there's my linear function. All right. Now, let's say I wanted to investigate this graph when x equals 1. Okay. So I've got this linear function. F of x is equal to negative 2x plus 5. I just chose something that's going to look very similar to this diagram you have over here. So let's say I'm interested at x equals 1. Well, what would I do if I said, okay, determine f of 1? Yeah, you just plug it in, right? So this would be negative 2 times 1 plus 5, and that would give me what? 3. So I know an ordered pair on this particular graph would be 1 comma 3. There's a relationship between the two. So what I'm going to try to show you right now is that as I get closer and closer to 1, okay, the unique value that this is talking about, it should be approaching what? Should be approaching 3. Well, let me see if I can show you that using a table. Okay. So I've got the graph here. Now, if you want to bring up a table of values associated with it, I like to hit Control T. So Control T. Okay. I know I don't have the calculators out because you guys were taking a quiz. So, I mean, if you have your own, fantastic. But if you want to write this down, just kind of follow along. So I'm going to have to change this a little bit because my increments are in 1. 1, 2, 3, and so forth. So I'm going to go to Menu, Table, edit the table settings. Now, I'm going to start the table in a different location, but I want my increments to be different. Let's slow it down. I only want the values to increase by 0.01 each time. Okay. Now, remember, the value of x I was interested in was 1, correct? Okay. So why don't I go ahead and start this guy at 0.5? Okay. So as we get closer to 1, what should those y values be approaching? They should be approaching 3. When we substituted in 1, we got a y value of 3. Well, let's see if this is what happens. Okay, so here is, oh, did I type that in wrong? Hold on, wait a second. I think I might have accidentally hit 5 instead of 0.5. Yep, 0.5, my fault. Okay, there we go, so 0.5. Okay, now look as the x values increase. So they're only increasing by 0.01 every time. But look at the y values that correspond to it. As the x values are getting closer to 1, what are the y values doing? They're decreasing. In fact, what are they getting close to? They're getting close to 3, that unique value L that the definition was referring to. And I can do this from both directions. If I go ahead and start at maybe, 2 or even 1.5, if I approach 1 from the right, I should be approaching 3 from below. That's what we're talking about here. Okay? As I get closer and closer to a certain value of x, what do the y values approach? That's what we're referring to as the idea of a limit. Okay? Does that kind of help out? Does that kind of make it a little easier? Perfect. Okay. Well, let me go ahead and dock him and be out of here. Well, what do we got? Okay. Now, to understand what it means for a function to be continuous from an algebraic perspective, that means, actually, what can I write down to actually confirm that it's continuous at a value? It helps to examine the graphs of discontinuous functions, or functions that are not continuous. Okay, functions can have different types of discontinuity, and we've actually been dealing with several of these already. First one is an infinite discontinuity. We know that as a what? That's a vertical asymptote. Okay, now we've actually been looking at limit statements, for vertical asymptotes. If you're looking at the limit as you approach the left and right of a vertical asymptote, what were the only two options? You're either going to curve up to positive infinity or down to negative infinity. When you're investigating the left and right side behavior of a vertical asymptote, you only have positive or negative infinity to look at. Okay, this other one is a removable discontinuity. All right, we know those as what? Holes, okay, and I'm going to go ahead and talk about this one more in a little more detail in just a moment, but let me show you the one that we haven't really seen. Okay, a function has a jump discontinuity at x equals c if the limits of the function as x approaches, bless you, c from the left and right exist, but have two distinct values. So this means if I start plugging in, if I plug in a value of c, okay, it's going to give me this point right here, whatever that is, this y value. Let's go ahead and say this is y1. Now, this y value that corresponds to the hole would be y2. So as I approach c from the left, I should be approaching y1, right? As I approach c from the right, what should I be approaching? That different value y2. This is what results in a jump discontinuity. Now, we haven't really dealt with these a lot. We saw them more with piecewise functions, but we were really just analyzing them at a particular value or just sketching them. Okay, so now we're actually going to have it as one of our discontinuities. All right, now one other thing I want to mention about the hole at the top of the next page. Notice that for graphs of functions with a removable discontinuity, okay, with a hole, the limit of f of x at point C exists, but either the value of the function at C is undefined, or as with the graph shown, the value of f of c is not the same as the value of the limit at point C. Let me explain what this means. As you approach the x value of a hole from the left or the right, the limit will exist, even if the function is undefined at that point. You remember when we practiced this, okay, when I gave you one of these sheets right here, we've got a hole right here at 3, what was it, 7/5? Okay. As I approach that value of 3 from both sides, the limit is 7/5. The limit still exists even though the point isn't defined at that location. All right. That's all that paragraph is talking about, something that we've kind of already seen before. Okay. So what does all this mean? How would I go ahead and determine if something is continuous at a particular value? I'm glad you asked. We're going to look at the continuity test. Now, there are 3 steps. Okay, they're laid out for you, very easy. Okay, so a function f of x is continuous at some value c, x equals c, if it satisfies the following conditions. Okay, so 1, this is really easy. F of x is defined at c. That is, f of c exists. That means I should be able to plug in the value of x we're interested in and get a corresponding value of y. Okay. Step number 2, f of x approaches the same value from either side of c. That is, the limit as x approaches c of f of x exists. So let me kind of talk about this guy for just a second. The limit as x approaches c of f of x. You'll notice c just represents some number, right? Some value. Typically for what we've done so far, it's been a vertical asymptote. But what have I been putting in place of a power every time we analyze one of those? A negative or positive. What does that mean? There you go. The negative means you approach it from the left, and the positive means you approach it from the right. Everybody's okay with that? Well, if you just have x approaching some number and there's no direction given, this notation is understood that you're approaching it from both sides. Okay? So this limit right here will only exist if the limit as x approaches c from the left equals the limit as x approaches c from the right. Okay? Only if I approach the same y value from the left and the right will this limit exist. Okay? That's what step number 2 is saying. Okay? Now step number 3, the value of f of x approaches from each side of c as f of c. So this is where you compare your results from step 1 to step 2. Does the limit as x approaches c equal the function evaluated at c? So step number 3, you're doing a comparison of the previous 2 steps. Okay. So again, that might seem a little hazy because right now I'm just kind of going through the steps. Let's go through a problem. Okay. Let's actually work with some numbers. Let's see if that makes it a little better. Okay. So right below this, I got this guy right here. Example 1. Determine whether f of x equals 2x squared minus 3x minus 1 is continuous at x equals 2. So they've given me a value of x. That 2, that's the c that all the instructions were referring to. All right. Now here's what I like to do. Every time I go ahead and start, I label them 1, 2, and 3. Okay, I label my steps neatly. But I always start by writing out a question to myself. And these are basically going to be answered with yes or no. The first one, and I always do this for every single problem. It's always the same. Does f of, now for step number 1, this is where you plug in your value of x, right? Well, what value of x am I interested in? Yeah, is it continuous at x equals 2? So my first step, does f of 2 exist? Or do I have some kind of issue at that location? Is there a discontinuity? That's what we're trying to determine. Okay, well, how can I figure that out? What is this actually wanting me to do? Yeah, just replace every x with that 2. So let's see, f of 2 would equal 2x squared, 2 times 2 squared, minus 3x, so minus 3 times 2, minus 1. So would I get a y value out of that? Oh, bless you. Ooh, that was loud. No, that's fine, that's fine. Thinking now everybody's looking at you. Everybody's looking at you. At you. I feel like I gotta explain all of them. Okay. All right, so what is the value? What's the y value? 1. Okay, so what do you think? Does f of 2 exist? Yes. Step 1 is looking good. Okay, so I can say yes to step number 1. Okay, now step number 2, the question is, does the limit as x approaches 2 of f of x exist? Okay. That's what you do in step number 2. But now, if I'm approaching 2, remember this limit only exists if the limit as x approaches 2 from the left equals the limit as x approaches 2 from the right. Only if I approach the same value from both sides will that limit exist. So for step number 2, what's really useful is if you create yourself a table, which I've already done for you. You'll notice what's right in the middle. It's right 2, the one that we're interested in. So what values did I choose on the left? 1.9, 1.99, 1.999. What are the values doing? They're getting closer to what? They're getting closer to 2. Okay. Look at the values I chose on the right. 2.01, 2.0, 2.001, 2.01, 2.1. So if you start at the end and come this direction, again, are they getting closer to 2? Okay. So what we're going to go ahead and do is take these values, we're going to plug them into the x's, just like I did the 2 previously, and we're going to get y values. I'm looking for a pattern here. As we get closer to 2, we should be getting closer to a specific y value. Okay. Now, I'm going to help you out with this. We didn't have the calculators today because of the quiz, but if I were to go ahead and plug in, for example, 1.9, f of 1.9, that would equal 2 times 1.9 squared minus 3x. So minus 3 times 1.9 minus 1. I believe you're going to get 0.52 if I'm not mistaken. Yes. That would give you a 0.52. Okay. And now you would plug in the other x values from your table one at a time, just like I did. So if I plugged in 1.99, okay, it's going to give me 0.95. If I plug in 1.999, it's going to give me 0.995. Now, this is something I like to do when I'm filling in my table because I'm looking for a pattern. Above, I always start at the end and work my way left because I want to see the pattern develop. I don't want to go ahead and start with, typically what should be the last number. Does that make sense? Okay. So if I go ahead and plug in 2.1, then I'm going to get a 1.52. If I plug in 2.01, I'm going to get 1.05. If I plug in 2.001, I'm going to get 1.005. Okay. Now remember, this is what the table is helping you to see. Okay. Below 2, this is the limit as x approaches 2 from the left. Above it, this is the limit as x approaches 2 from the right. Okay. Well, look at your y values. As I get closer to 2, 0.52, 0.95, 0.995, looks like the y values are getting closer to what? Okay. So I would say the limit as we approach 2 from the left is 1. Okay. Now, as I start at the end, 1.52, 1.05, 1.005, what's the limit as I approach 2 from the right? 1. Okay. So here's my question. Does the limit as x approach 2 exist? Yes. As long as you approach the same number, whoa, interesting, from both sides, then that limit exists. Yes. Okay. Now we're on to the final step, step 3. Okay. Well, this is where I'm going to compare the results from the previous 2 steps. So step number 3 is always going to look like this. Does the limit as x approaches 2 of f of x equal f of 2? Remember, this limit is what we were looking at in step number 2. F of 2 is what we got from step number 1. Okay? So does the limit as x approaches 2 of f of x exist? We said yes, and we got 1, right? What did we get in step number 1 when I plugged in 2? F of 2 was what? 1. So does 1 equal 1? Yes. Because of this, is this function continuous at x equals 2? Yeah. That's all it means. So I can say because of this test, it's continuous. There is no type of discontinuity when x equals 2. Okay. Now tomorrow when you come in, after we talk about the quiz, we'll go ahead and start looking at some problems like this one below that are going to have issues. They will have discontinuities. And the table is going to help me determine which type of discontinuity based on the patterns that I see. Okay. All right. Cool. Thank you very much.